In this video, we're going to look at saturating a transistor and what that really means and the mathematics behind it. So in the last video, we saw that we had this circuit here with our beta value equal to 100 and we're using an NPN transistor. Now what happened is if we assume that the collector current was equal to beta times the base current, well, we found that VC, which would be equal to VCE, was equal to minus 455 volts, which is extreme. Does not make sense. And this led us to the realization that we're not in the active mode or the cutoff mode, but perhaps we're in the saturation mode. So if we determine that we're in the saturation mode, well, how do we deal with it? And to that, we need to examine a few things. And those will be the input and output characteristics from the datasheet of the BJT. Now, generally, with your input characteristic, you're going to be looking at the base current and VBE. Now the output characteristic, or perhaps characteristics, we're going to be looking at the collector current and then VCE, or the voltage between the collector and the emitter. Now we're going to have a few different plots here, and they're going to be dependent on what the base current is. Now what you can see here is if we consider the case where the base current is 50 microamps, if we have VCE greater than 0.2 volts, well, what do we get? We get that the collector current pretty much flatlines at 5 milliamps. So if VCE is greater than 0.2 volts, we have IC being equal to 5 milliamps. Divide that by IB, which is going to be equal to 50 microamps. And this is constant no matter the value of VCE. So what we can say is that this is what we're going to call the active region, where the collector current flatlines. And then if we consider the case as the base current goes to 0, you can see here we start at 50, 30, 10 microamps. If we were at 0, we would have something that is pretty close to 0, which would mean IC, or the collector current, is also equal to 0, and that's going to be no matter the VCE value. Now for VCE less than 0.2 volts or equal to 0.2 volts, what we get is that the collector current divided by the base current is no longer a constant. So if we consider, again, this 50 milliamp base current, if we consider VCE being equal to, call it 0.15 volts, we get, call it IC, is equal to 4.25 milliamps, and then IB, that's going to be equal to 50 microamps. Now if we take this case, call this 0.1 volts, we get something like IC being equal to 3.5 milliamps, and IB being equal again to 50 microamps. So what we could say is that this value for the 50 microamps would be beta 1, and this value here for VCE being 0.1 volts would be beta 2. So we would have different beta values or different gain values depending on what VCE is. So that's going to be our saturation region, anything to the left right here. And what we'll often see is that if we assume the saturation region or the saturation mode, we approximate VCE to be equal to 0.2. Now, distinguishing from the classroom versus reality, if we look at the datasheet for the output characteristics, you can see here for IB, or the base current being equal to 40 milliamps, we do get a pretty nice flat line. It's not so bad even at 60 milliamps. At 80 milliamps, we start to pull away from that, and then by the time we get to a base current of 200 milliamps, you don't really even see that flat line anymore. So in reality, things aren't ideal, and the analysis is a little bit more complex. But nevertheless, if we consider this kind of 0.2 region here, call this 0.2 volts, but because this value is so small, that's where that approximation of 0.2 volts comes from. So how can we apply this? Depending on the circuit of the BJT that we're given, if it's in the NPN configuration, we have to start with an assumption. Now, the assumption is kind of like what we did with the diodes, except we have to assume a state, and we have 3 states to work with. It's going to be the active, the cutoff, and the saturation. Now we know for the active region, or the active mode, VBE, it's going to be 0.6 to 0.7 volts. VCE, we're going to expect that to be greater than 0.2 volts. Our collector current, we can approximate that to beta times IB, and we probably don't know what our base current is. That's what we're going to have to find. Now if we're in the cutoff region or cutoff mode, typically VBE is less than 0.6 volts. We don't know what VCE is, probably what we're going to have to find, and we assume that IB and IC are equal to 0. Now if we're in the saturation region, VBE again is 0.6 to 0.7 volts. We make the assumption that VCE is 0.2 volts. We usually have to find collector current or the base current or the gain. So let's go into an example, and we can come back to what we were working with before. So we know that we're not in the active region, not a possibility. So what can we do? Well, let's assume saturation and see what happens. If we look at the base current, we simply know that we're going to have that 0.6 volt drop from base to emitter, and the emitter is tied to ground. So we can say that the base current is simply 10 minus 0.6 divided by this 10K resistor right here. Get that our base current is 0.94 milliamps. Now because we're in saturation, we're going to assume that VCE is 0.2 volts. So because VE is tied to ground, we know that VC right here will be 0.2 volts. And from this, we can find what the collector current is. So the collector current is going to be 15 minus 0.2 divided by this 5K resistor right here. So that's going to give us our collector current, and that's going to be equal to 2.96 milliamps. Now what we can then do is find the beta or the gain for the saturation, and that's going to be our collector current divided by our base current, or 2.96 milliamps divided by 0.94 milliamps, and that's going to be equal to 3.149. Now what you can notice from this is that the saturation beta or the saturation gain is much, much less than that defined gain that we had. And if we look at a simulation, so I tried to throw in a transistor that had an approximate beta of 94, close to the 100. I tried. But what we get is in the green here, we're looking at our base current, and in the blue, we are looking at our collector current. What we can see is that the base current is approximately 0.94 milliamps, and then our base current is about 3 milliamps. So we're pretty spot on, not too bad. We hit our target, and the simulation verifies it. So from this, it's confirmed that we are in the saturation mode. So what happens if we just always assume saturation? How will that steer us in the wrong way? Well, let's consider the other circuit from the last video, which we found out it was definitely in the active mode. It passed all the criteria, but let's say it's saturated. Now from that, we're going to say that VCE is equal to 0.2 volts. We know that VBE is going to be equal to 0.6 volts. So from this, we have 4 volts here. We have a 0.6 volt drop between the base and the emitter. So we'd have 3.4 volts right here. We could say that the current going through this 3.4K is going to be equal to 1 milliamp. Now if we say that VCE is equal to 0.2 volts, that would mean that VC is equal to 3.6 volts. Everything is still okay for now. And now we can look at the collector current. So what we can say is we have 10 minus 3.6 divided by that 4.7K resistor, and that gives us a collector current of 1.36 milliamps. Now if we look at VC, we can see that that's equal to 3.6 volts. VB is going to be equal to 4 volts. VE is going to be equal to 3.4 volts. And everything might look okay here, but let's do a KCL. So if we look at this current going into the transistor is our giant node. That is 1.36 milliamps. Going out, this current through this 3.4K, that's going to be equal to 1 milliamp. And the only way that this really makes sense is if we had some current going in this direction for the base, which was equal to 0.36 milliamps. Well, what happens if current is going out of the base for the NPN? So if this circuit really is in saturation, it means that our base current is going in the opposite direction and we're still functioning as a normal transistor. Doesn't make too much physical sense, but you really have to go through the entire circuit here to see that this assumption up here was incorrect. So this video should be quite helpful in basic BJT analysis. In the next video, we're going to look at the load line analysis of a BJT, similar to what we did with a diode, but obviously it's a little bit different now. Thank you for watching. If you learned something new or found something useful, please like, comment, share, subscribe. Helps the YouTube algorithm.